Welcome to another week of lectures on state space control. We estimated all the states in the previous lecture and we derived the following control law, but in this week we will estimate only the missing states. If you recall, previously we estimated and used it in the control law directly. We did not use this planned measurement in the control law. In this week we will estimate the missing states and we will use a controller of the following form: the measurement y used directly as a part of the control law. Only this part is estimated. What is not measured only is estimated in this week. How do the pole placement methods of the polynomial and state space approaches compare? We will show in this week with a double integrator example that state space method with deadbeat reduced order estimator, that is with all the poles at the origin for the estimator, will be identical to the polynomial method that we derived earlier few weeks ago. In both cases we will find the control law to be of this form. Engineers like integral mode. Can we introduce it in the state space approach also? We will consider an augmented state space equation where we have introduced an extra state x sub I, and we will use the control law as follows. This is the usual state space control Kp into x, but now we will use this extra term Ki into xi of k, and we will demonstrate the efficacy of this with a Q system. Next we will move on to linear quadratic regulator. Given a discrete plant, we will find a UK minimizing the cost function given here. We will have matrices Q1 and Q2 which are symmetric, which play the role of tuning parameters, because in the pole placement controller we need to come up with pole locations. Instead here we have to tune with Q1 and Q2 matrices. We will augment that index with Lagrange multiplier as given here. We will differentiate with respect to u, lambda and x and arrive at these equations, and after solving we will arrive at this solution, which is a 2-point boundary value problem solution. With this method we will also calculate the optimal index right at the beginning. We will also calculate steady state control law by a different method using eigenvalues and eigenvectors. We assumed in the previous slide that the state was measured, but as mentioned earlier the states are not measured. What we will do is we will use Kalman filter as an optimal estimator of states. In fact, Kalman filter plus LQR is LQG. LQR is linear quadratic regulator that we saw in the previous slide. When we combine these two we get linear quadratic Gaussian controller or LQG, but we will not cover Kalman filter in this course. We have allocated only 2 weeks to cover state space approach. Normally state space approach is covered in an entire course, and there Kalman filter is covered. State space methods provide an alternative approach to the polynomial technique. State space approach is more popular with the theoreticians. Many more results are available for state space methods, but engineers who are used to transfer functions find the polynomial approach more natural. It is important to point out, however, that both approaches are equivalent. Welcome to the lectures in this week. There are many exciting techniques that we will develop. We would want you to go through these lectures and benefit by them. Goodbye for now.